Morning. My name's Jim Armstrong. We are going to take you through the whole pulp making process, and we start off with chips, and I'm going to show you some samples of the chips. The very first thing that we have to do is to screen the chips so that they aren't too big and they're not too small. They're just about whatever size we specifically need. There's a bag down here of the chips, and these ones you can see. This chip here, you can see how it's kind of cut like that. That's coming off a chipper blade. And the chipper is located right behind me. This great big machine back here. And we could put 2x4s down here, and then the blades go spinning around. They just literally are slicing it off. Okay. These are all very small compared to industry. They're monster machines in industry, but this is for lab purposes. So looking at the chips, there's some long ones, there's some really short little tiny bits, and what we want to do is we want to screen it out. We want to get rid of the little tiny bits, not interested in that. We don't want these big bits. We want chips that look something like that and that and that and that. So those are good samples of chips. To do that, we use a screen, a shaker screen. We'll go around the other side, and this shaker screen is the same type of screen that would be used in a gravel yard, where they pick up front end loaders, grab the stuff off the side of the mountain, and they simply dump it on here. And you've got different size grates. These are larger holes. The chips we want are going to go through there. These ones are smaller, and will basically, whatever slides across the top is going to be acceptable. Also, if it gets through here, it gets down to here, anything that goes through this guy is junk. By junk, I just mean that we don't want it in our pulp cook. We would use it in the pulp mill for other things like fuel for the hog boilers, etc., 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 to make steam. Anyway, so the stuff that comes off of here and off of here is going to land on our floor. In the mill, this would be dropping onto a conveyor and go up into a chip silo, and the screen chips would sit in that chip silo until they're needed over in the digester. So I'm just going to start this up so you can see how it works. All it is, it's just a motor sitting on here with an offset cam on it, and it causes this thing to shake. So now you'll see it starting to vibrate. Okay, and you can see there's still little tiny bits of wood stuck in there. And these things will shake off of here and drop down. The fines are going to end up going through the bottom one and back in behind. The accepts will come here. Normally there would be another plate on here to catch the big ones, but we just simply grab them as they're coming along. So I'm going to go now, and I'm going to get some chips, and I'm going to feed them up on the back, and the video you'll be able to see how the chips are coming down and how they're getting separated. Okay? So this is very manual. In a real plant, there would be a feeder coming in and dropping it down through here. So there'd be a chute, and they would just slowly feed them in. I got to do it by hand. So I'm going to grab a handful of chips, throw them on there, and Charles, if you go around that side. So now you can see our good chips are coming out there, and there's one of the big pieces that I didn't want. Another one, another sliver. But in general, most of them are pretty good. Even this guy that's a little bit on the long side, that would cook quite easily. That's not going to be a problem. And so those would be acceptable chips to now go into the silo, and then from there they would draw them out to use them either in a continuous digester or in a batch digester. Okay. So while I'm here, you can see this is the counterweight. See, there's lots of weight on this side, nothing on the top. So when this spins around, it offsets. And we'll fire it back up again so you can see how it works. But down underneath, I wanted you to see the fines that are coming through from the lower screen. Those are rejects. So rejects there and rejects off the top. The middle two screens are our accepts. Now I'm going to start this guy up, keep my fingers out of the way of that belt. And you can see now how that offset weight causes this thing to shake. And I'll slow it down. And you can see how that offset weight really causes this thing to shake. And this whole thing is just sitting suspended on 4 springs. So it's kind of like the springs of a car. Okay. Okay, we're in the Pulp Lab, Pulp Digester Lab. And behind me here is our white liquor storage tank. We added some sodium hydroxide crystals, and we added some sodium sulfide to that, and mixed up a mixture, and the tank is just about filled to the top. I don't know whether you can see it in there. And that shaft that's going down with this thing up here is an agitator, which we don't agitate it very much, or it can wreck the liquor by drawing in carbon dioxide from the air. In a pulp mill, they actually, when they're mixing this stuff up, it cascades down on a device like this. So it actually will overflow from one to the next, to the next, to the next. You can see how it goes underneath and then overflows, and underneath and overflows, and underneath and overflows. It's called a classifier, and that's where they actually do the mixing. So it's not strong agitation, because you don't want to pull air in. Now I'm going to take a sample of this liquor. Normally you would stir it, but I don't want to stir it too much. I'm just letting the drips come off the end. This is a very caustic solution. I will show you a little bit later the damage that it did to my arm. I got just a drip of this stuff that when we were mixing it jumped up on my arm, and I don't know how well you can see, but there's no hair left there. And then you can see a couple little marks on there, and this is from 2 weeks ago, but in a matter of minutes it literally dissolved all the hair that was there. And I think it got exacerbated by my watch rubbing back and forth on it. At any rate, I didn't get a bad burn, but I did get a burn. So you want to be very careful with this stuff. It's nasty. Okay. So in a pulp mill, the recost operator, the operator who's looking after the area that is making the liquor, runs tests on the liquor. And what he's looking for is to find out what the causticity is, what the alkalinity is, what the activity, sulfidity, the number of things he needs to know. And again, that's done by the operators, but we as technicians who are actually controlling this thing need to know the background behind it. So we've got a laid out procedure for the testing. We basically take one normal hydrochloric acid, and then we use a phenolphthalein indicator and a methyl orange indicator. We also need some 20% barium chloride. There are 3 tests, and laid out on the sheet here, you can see test A, test B, test C. And all it is that you'll take a sample and you'll put in an indicator, methyl orange, and then you want to see how much 1 normal HCl you have to add before it changes color. Okay, and in fact, that is the first test. So we're actually going to take 5 milliliters of white liquor sample, add a couple of drops of water, and I usually like to use 2 mils. So this is deionized water, and squeegee, there it is. This little bulb is quite complicated. There's valves all over it, so I just push one of them to vent the air out, and now you can see it's ready to suck, and when you push on this one, it actually will pull air up in here. So what we're going to do is we're going to get a 5 milliliter sample. This is called a pipette, and it's got a little mark on it somewhere right there, okay, where my fingernail would be if I didn't have a glove on. And so you're going to fill it up to there. So I'm going to take this guy, squeeze it down, that over the end. And then I'm going to pipette in 5 mils. Okay, that's my 5 mils. I should be sitting right on that line. Now, my 250 mil Erlenmeyer flask, where did I put those guys now? Didn't I bring them out here? Okay, this is an Erlenmeyer flask, about 200 mils. This one is actually a graduated one at 250. We'll need this for test B. So now what I'm going to do is I'm going to add the 5 mils of white liquor. And you might notice, I don't know how well it'll show up in the video, but Charles, just look at the color of that. It's kind of got almost like a lemon color to it. Okay, so that's my 5 mil sample. Then I want to get 2 mils of water. So this pipette is 2 mils right to there, the zero line down to there. This is 2 mils. So we're going to pipette that up into here. Too much, but we'll dribble it out. Here's my 2 mils. And so that's got to go in with water. So now this burette is filled to the zero line with 1 normal hydrochloric acid solution. I made this up. I had an ampule of concentrate, and once I diluted it into 1,000 milliliters solution of water in that concentrate, it is guaranteed to be at 1 normal.
Indicator.
Okay.
Indicator.
Yeah, the indicator, yes. This is methyl orange. The other one that we will need in the test B is phenolphthalein. These guys actually, the methyl orange endpoint, when it just turns red, is between 3.1 and 4.4 pH. Okay, so I'm going to put 3 drops. One, 2, 3. See, it's kind of an orange color, hence methyl orange. And then what we're going to do is we're going to add acid to it until it turns red in color. And you kind of mix it while you're doing it. You can see a little bit of pink started to appear there. See it, but it goes away. Still going away. Still going away. Still orange. Still orange. Getting close. Very close. Right there. And so that took 15.4 milliliters of acid. So that's the first test. So typically, I would write that down onto a spreadsheet. And what did I say, 15.4? Well, the last time I tested it, it was 15.5. So it's pretty well the same, which it is. It's the same sample of liquor. So what that does, that the sodium hydroxide, sodium carbonate, sodium sulfide all react with the HCl, one normal HCl. Test B says we're supposed to pipe that 50 milliliters of white liquor. Now I'm not going to go through this. This takes quite a while. But we would take 50 milliliters of that, put it into this graduate, okay, which is graduated at 250 mils. Then what we're going to do is we're going to add 50 milliliters, which is why I've got 50 milliliters of 20% barium chloride, this stuff, which was made up in 2019. And we put that in there. Then we top it up to 250 mils. And we spin it around and shake it. Typically you put some paraffin film over the top of it, wiggle it back and forth, and it'll be kind of chalky white. Then the next thing you do is you take a filter and put it into a funnel, and you pour this stuff into it. And you wait for the clear liquid that comes out the bottom. It's called supernatant. Then you now take that supernatant, okay, and you bring your burette back up to the 0 mark with acid. Then you titrate it with phenolphthalein endpoint. Well, that endpoint is between 8.3 and 10 pH. And you record that as the number of mils. So in the test that I did, and we're going to be really close, it took me 13.5 mils of acid added to bring that supernatant up into a pH range of 8.3 to 10. Okay. Then we record that down. Then what you do is you had phenolphthalein in there as the indicator. Now you go and you add methyl orange, and you continue titrating down, and it usually only takes a couple more mils, and in this case it went from 13.5 up to 15.9. I recorded the 15.9. Then all the math buried in behind this spreadsheet calculates out everything. Now normally the sodium carbonate is about 0, and this was just a little bit on the negative side, so I'm not concerned about that. Sodium sulfide, you're going to see in the PowerPoint that we're going to go through, 30 is the target. We're sitting at 29.76, so we couldn't be much better with our white liquor. Sodium hydroxide, 68. The other one that we're really interested in is the active alkali, and this is the alkali that actually dissolves the lignans, okay? And this is 98.58, which is a pretty good number. Typically you want to be 75 to 100. So this acid indicates that it's fairly concentrated. The other things we're interested in is the activity and the sulfidity. And the sulfidity, we're supposed to be at 30, we're at 30.19. Okay, so by all counts, this liquor is pretty good liquor. Okay, and this lab test will be done. The things we need to know are the specific gravity, which actually is measured in Baumé, and if you guys remember back to all your density stuff, Baumé heavy scale, it's 14.7 degrees Baumé, which works out to be 1.13 SG, and 113 SG. We are using a Coriolis mass meter to meter in the amount of liquor that we need, and so therefore we had to, these calculations normally are done for volumetric, and we had to do it in mass, so that's why we need the SG, was to correct for that. Other than that, we're basically ready to go. Prior to the cook that we're going to do, we need to know what the moisture content is of the chips. So what we've got is we've got a tray here, and that tray is tray number 1, and it is 110.15 grams. Tray number 2, well actually we'll do them one at a time. So we're going to take some chips and put them in there just to put a little bit on the bottom. you look at these chips, you see they should look wet, and they are. That's why we keep them in bags, to make sure that we don't dry them out. That's probably plenty right there. So the weight now is 243 with green chips. It's 243.60. And then we're going to put these in an oven. But we'll make sure we don't mix them up. I'm going to take another one, tray number 2. Just zero that. Tray number 2 is 113.19. We'll put some chips in there. $234.74. Number 3. Now we're going to take these ones out of the second bag. What we're going to do is we're going to average all of these. That's a knot right there. It's not going to cook very nice at all. We'll get rid of it. There's the other half of that knot. That's 221.73. What did I say the weight was first without the chips? Did I do that?
You didn't really know.
Number 3, 106.47. $232.08. Okay. So tray number 4 is wow, real difference. 94.65. Less metal in that one. Mm-hmm. $230.34. Okay, so now these guys got to go up in an oven, which I'm hoping is running upstairs. So we're going to just go up into the upper lab. So this is sitting at about 110 degrees Fahrenheit. right now. Oh. Well, didn't clean up after themselves. That's hot. Jeez. So we'll catch that in the morning and we'll get the weight. And it's much like doing a consistency test. So what we're going to do is we're going to get the dry weight of the chips and the tray. We'll subtract the tray from each of them. That'll tell us what the green weight was and what the dry weight is, and from that we can calculate the consistency. And we're going to do that in the morning. Okay, so what we're going to do this morning is we are going to weigh out these trays and then figure out what the moisture content is. And this is tray number 4, and his total weight, when we did it yesterday, tray number 4's weight was 230.34 tray and chips. Now it is down to 154. 154.18. Tray number 3 has dropped from 232.08 to 160.59. Tray number 2 has dropped from 234.74 to 166.36. And tray number 1 has dropped from 243.60 to 168.74. So we'll calculate the amount of water that has been removed from that, and what we're after is not the amount of water that's in there, but the amount of fiber that's left in there. What we're after is we need to know how much bone-dry fiber is in. We do want to know how much water's in there. That's part of the calculation as well, but we are cooking the chips, not the water. Okay? Okay, so we're up at the computer right now, and what I've done is I've taken those weights, which we just did, the dry weights, and you can see them there at 168.74, 166.36, 160.59, 154.18. It subtracted the weight of the chips from the tray from the dry weight, and it now worked out the amount of water. Okay, and then it inverts that because we're really after the amount of fiber, and it came out at 43.95, 32.66, 43.09, and 43.87 for the 4 samples that we did. The average of that came out at 40.89. That seems a little bit on the wet side, although the chips did feel wet. Typically it's more like about 46 or 47, but we're going to go with what we got and we'll see how that works out. Okay, so that information is needed as we enter data into the DCS next. Okay. So what we're going to do is we're going to follow the instructions in detail, and what they tell us, and this is in the documents that you have, they tell us to weigh out a chip charge. So the first thing we got to do is go downstairs to the scales, or actually the cooler, get the bags of chips, take them over and weigh them. And they told us item 2, do a moisture check, which we've just done. You've seen that information. Perform a titration. We did that previously. You saw that as well. And then we've got to start up the room and blow tank fans, turn on the 24-volt power in the cabin, and then turn on all the electrical disconnects. So there's some mechanical things that we've got to go do now. Okay, so we got the first bag of chips on the scale. Typically we want about 66 pounds, and then we'll convert that into kilos. This first bag is sitting at 38.1. So I'm going to put a little note on here. 38.1. Didn't mark very well. Do it again. 38.1. Second bag I think is a lot heavier. This bag is running at 49.1. Okay, now while we're down here, I want to start the fans up. So over by the wall, we have 2 fans. One of them is a general exhaust fan, which takes air out of the general room. The second one is over the digester blow tank. And while I'm down here, I'm going to start up the booster pump. We actually take city water pressure, which is around 40 psi, and push it up to 140 psi for use on the gland water seal on the liquor recirculation pump. At startup, there's no pressure in the digester. But as we start cooking, the pressure will rise, and we need to have enough water to overcome the pressure in the digester. The digester pressure will come up to about 100 psi, and with only 40 pounds of city water for gland water, we wouldn't have sufficient. So we boost it up by 100 psi to get 140 on the seal side with the 100 pounds of fluid, liquor and water inside the digester. Okay, so I'm going to start that guy. Okay, so we're up at the batch digester. This is a little tiny baby. This one is only 3.5 cubic feet. Typically, these things are about 2.5, 3 meters in diameter at the top here, and they're probably 40 meters, 50 meters high. So they're significantly larger. So what we're going to do, I don't know if you can get the camera down there, but down in the bottom, you might see where the light is that there's like a silver ball down there, and that's the ball valve, which is closed right now. And then just up from that, there's some screens. And I don't know whether my laser will pick up on your thing or not. But where my laser is pointing right now, those are screens. So the liquor is going to get sucked out through the screens, the chips stay behind. The liquor is then going to come up and it's going to circulate and come out these holes. And jets of liquor will be then pouring down over the chips. Now, we have to put the chips in here, and when you view the videos later, you'll see that there's a variety of ways of packing on standard digesters. They can steam pack them, they can liquor pack them. Typically steam packing is used, and what they're trying to do is to get the chips so that they're packed in there and there's no voids, that it's all filled with chips, and yet the liquor can still circulate through. So we don't have any of that stuff on here, so what we're going to do is we're going to carefully put these chips in, not dump them in. I don't want to get any voids in there. Okay. Okay, so we managed to put in 1 bag of chips, so we got 49.1 pounds in there. And if you look down into the digester, you can see the chips in there. And it's not quite full. Normally we bring it up to about 2 inches below the bottom jet. So right about in here somewhere. Okay. Okay, so now you can see we've got our chips in. We're just nicely below the bottom jet, and there they sit. And what's going to happen is when we're going to seal this thing up, we're going to put liquor and water in here based on how much it tells us to. And then when it's running, the liquor is actually going to come out of those jets, land on here. The angle for the lower holes is set that it'll kind of shoot a ring down around in here. The upper holes try to shoot closer to the center. So you get some liquor distribution. Okay, it's good. Okay, so this guy was 38.1 pounds, and now he is 18.3. So we used 19.8 pounds out of this bag. We'll seal this back up and put it back in the fridge at a later point. So we've got our chips in the digester. We haven't buttoned it down yet. We've got our moisture analysis done. We did the titration. We got the fans on. You need to turn on a 24-volt power supply and some disconnects. So over here, the light is already on. We have a 24-volt power supply right here, which is energizing all the relays that we're going to bring in for contactors for starting and stopping stuff. We have that independent so that it doesn't accidentally start itself up when we're not here. So we turn the power on. Now we need to go get the disconnects. Go over this way, back through. We're going to use 3 disconnects, low tank agitator, which is the first one hand and looking the other way when you turn it on. The second one, the mixed tank agitator, that one on. The third one is white liquor transfer pump liquor from the white liquor tank to the digester. Turn that one on. And lastly, the liquor recirculation pump, which is going to circulate the liquor around into the digester. Okay. So what we're going to do now is we're going to check a couple of things. I'm going to go into a digester charge system, and there is my white liquor tank and my white liquor pump. I just want to give it a stir for a few seconds. So I go to the mixed tank agitator, and the requested state that I'm going to select is there. Currently it's asking for stop. I'm going to toggle it. You can hear in the background the agitator come on. If I go back to previous display, you'll see the agitators now mixing the tank up. I don't want to aerate it, so I'm not going to leave it running very long. As a matter of fact, I am going to shut it back down now. So I go back, the current state is start. I'm going to select it. It turns yellow when it's selected, and I'm going to toggle it. It went for stop, and the status came back as stopped. Okay? So now I want to go back to previous display. So we're going to now try and figure out how much liquor and water do we need. So to do that, page 2, it says, or page 46 in your booklet, it talks about weighing out the chips, which we've already done, and it wants us to next go over and evenly torque down the lid. So let's go over to this thing. So we used the torque wrench and we crisscrossed and tried to get it nice and uniformly pushed down. There's a rib sitting on just on the underside of the lid, which actually pushes into the gasket, which is sitting in a recess around the top. Just before we put the lid down, I ran my finger around there to make absolutely certain that there was no bits of wood or chips stuck in there, because then you'll start getting vapors leaking out through here, and it's nasty stuff. Black liquor is not to be toyed with. Anyway, I'm going to give these guys an extra crank with a hand wrench. You can see that I got something on it, and it doesn't, you don't have to crisscross on this, they're already down. Just a matter of making sure that it's good and tight so we don't get any leaks. So we torqued down the lid, you saw it being torqued down, and now what we have to do is enter data into the computer. It will do calculations. Now I've actually got a spreadsheet running on my laptop which will calculate all the charge calculations, which is normally done by the operators, but it's sort of a backup. We also have calc blocks buried in the Foxborough IA DCS system, and if I go into, well, let's get the data in first, then I'll show you where the calc blocks are. So we have to go to a pick on here, which is operator input calcs. What I did here was to use analog input blocks. They're just AI blocks. And once you've done the Fox IE stuff, you'll know that the measurement is the real-time data coming in, and then this is the output going back out. I left these blocks all in manual. They never go to auto. The calc blocks down here do, but these blocks in here do not. What we can do is we can actually enter the raw data in. So the green weight charge of chips, we worked that out to be 31.252 kilos. It was 68.9 pounds. You remember I had 38.1 in the one bag. The second bag I put on, after we dumped chips in, we still had 18.3. That gave me 19.8 pounds that we used out of that second bag. And the first bag we used all of it, so it's 49.1 pounds for a total of 68.9, which converts to 31.252 kilos. So I'm going to put in here, I've got a little operator window down there, and I'm going to enter in, my number's lock on, yes, 31.252. That number actually goes into the computer. The display only indicates to 2 decimal points, okay, and they're all set up that way. The second thing that we did was we ran a check on moisture, and so we calculated what the moisture was, and it came out at, it's over on my computer over here. So I go back. It's that one there, and it calculated at 40.89% bone dry fiber. Okay? So that's the number that this guy wants. And you can see the last time we ran on, it wasn't that much different. It's 42.49 the last time we ran it. This time it's, what did we just say, 40.89? 40.89. And so that one in there. Now, while I was doing this, these calculator blocks are actually calculating how much liquor and how much water do we need to put in. For example, I'm just going to play with this for a second. I'm going to move that out to 50. I'm going to say we got more wood in there. So if I put it out at 50, watch the liquor and the water. The liquor went up and the water went up because we've got more bone dry wood in here. We need more liquor to cook it, and we need more water to maintain a liquor water ratio of 4.5 to 1. In the PowerPoint that I'm going to go through later with you, you'll see where these numbers are coming from. Depends on the type of fiber that you're cooking. For softwood and hemlock, which is what we're doing, normally we run 18% active alkali on bone dry wood, and normally we run at a liquor to wood ratio of 4.5 to 1. When we get into hardwoods, those ratios change a little bit. Active alkali of the liquor. Earlier we looked at the titration sheet and we did an ABC test on it, and the active alkali came out at 98.58. So I'm going to go down here and I'm going to tell it that it is 98.58. Now before I actually hit the enter key, look at the liquor. Now the liquor that was in there was nowhere near as active in the last calculation. This is more active, which means we should probably need less of the liquor. And sure enough, the number dropped down. It went from 38 down to 31 because this liquor is a more concentrated liquor than the liquor that we had used in the last cook. And then we need to know the specific gravity of the liquor because we're using mass flow meters, not volumetric flow meters, to measure the amount of liquor and water we're putting in. The liquor was measured at 14.7 Beaumet with one of these guys. You guys remember this. This is a hydrometer, but the scale on this one is Beaumet scale for heavy liquids, reference to 60 degrees Fahrenheit. And so I actually measured it at 14.7, which is right there where my fingernail is. And that then converts out to 1.113 SG. And you guys all know how to do that because it's in your notes. If you don't, go look. So 1.113. And it, oops, I must have hit a bad number or something. Oh, ha, I put it in the wrong one. Look what happened to that liquor charge. Okay, so I got to go back. My active alkali was 98.58. Oh, that. Okay, that's better. And the specific gravity is this guy here, and he is 1.113. And it changes it minimally. Now, that's the calculations that this guy has done, and this is using calc blocks. Now I've got Excel, I'm making notes for myself here of what to put in. Oh, wait a minute. The moisture content was 40.89. And again, it's changed the liquor, it's changed the water, okay, based on that. Because we told it we've only got 40.89% of bone dry fiber going in there, so it needed less liquor for it, but it had to up the water because it needs to maintain a liquor to wood and an active alkali on wood ratio. And those calculations are all buried inside of a calc block, which I will show to you later. So over to my display. Laptop, I've got a spreadsheet running to check this. Minimize that. Where's my spreadsheets? This is that guy. Okay, so the amount of chips that we put in there, we said was
68.
Actually, is that what we said? 68.252, wasn't it?
68.9. Oh, you want it in kilos?
Yeah.
31.252.
That's better. $31.252. Okay, so on the Excel spreadsheet, I entered in the amount of bone dry fiber, the 40.89%, and I entered in the green weight. Based on the percent bone dry, it calculated the amount of water and the bone dry weights, The 4.5 to 1 liquor to wood ratio is normal. The total liquid weight is a matter of taking the water weight and adding that to the amount of water that we're going to put in, and it'll come out to 57 kilos of total liquid. I had to enter in the active alkali, 98.58 grams per liter is sodium oxide by analysis. SG 1.113. It calculated total weight, chip water weight comes from up there, and then it calculates the amount of white liquor and the amount of water required, and it is exactly the same numbers as we got on that Foxborough DCS. Okay, so we've entered all of our data in. Now, you see here where it calculated the liquor charge, where my mouse is, where the cursor is, and there's the water charge. Well, if I go back to liquor charge display, the graphic of it, lo and behold, there's my set points of liquor and of water. Okay? Now, we're going to let the computer actually do all of this. It's going to control it so that we don't overfill or overcharge it. We've got some special software that we set up to do that. So the next step in here tells me to go down to the transfer pump and bring it on. So I'm going to go down to this guy right in here. It says, actually I can go to the liquor charge group, and it says the liquor, and I want to look at this controller. This is going to control the mass flow of the liquor and the water in. It should be in remote, and it's in manual right now. Its output is at 0. It's got a set point coming from some background computer blocks of 4 kilograms a minute. The next thing we're going to look at is that we want to take and determine what we're going to put in first. So if I go back to the graphic, it's going to hit previous display for a second. If I go back to the graphic, currently the liquor valve is active and the water valve, domestic cold water, is not. Now, basic chemistry. Do you add acid to water or water to the acid? Well, the answer to that is you add the acid to the water. And the reason for it is that it's exothermic. It'll generate a lot of heat. If you put the acid into the water, it will literally, if you put the water into the acid, it will generate heat in the acid, and you'll end up with it splattering and coming out all over you. So we want to put the water in first, and right now we're selected the liquor. So I'm going to go back to the liquor charge system. In the liquor charge system, I've got a solenoid valve that I'm going to activate. And when I've got it in the open position, it means I've got water. And when I've got it in the closed position, it means I'm on liquor. So I'm going to select it, and I'm going to change it. And you probably won't be able to hear it, but those of us in the room could hear a little click as the solenoid actually switches over. Very hard to hear, and I'm going to click it back again. It's happening, but it's very, very difficult to discover. Also, there's totalizers, totalizing the liquor and totalizing the water. Right now I'm selected on water. So this one is cleared and it's ready to run. It's the same flow meter. We're just going to put the water through, then we're going to put the liquor through. When we switch over to liquor, by toggling that requested state, you'll notice that the hole switches over to this one. So now the water totalizer is held, it won't count, and the liquor totalizer is now going to count. And that's how we're going to know how much water and how much liquor we put in there. So I'm going to go back because I want to put water in first. So I'm going to select that and toggle. The other thing we need to do, although it's already done, is that we need to clear the totalizers. Now, we just did a reboot on the computer, so they automatically got cleared. But the process would be to click on the clear button on the liquor charge and then toggle it. And if there was anything in this register, it would go to 0. Then you go over to the water charge one and you select clear, and now you toggle it. And if there was anything in that totalizer, it would be cleared out. Okay? All right. So the next thing to do is to look at these blocks. And what's going to happen here is that we've got to start up our pump, okay, which is the next thing it wants me to do. I'm going to go toggle. The pump comes up. Oops, wrong pump. Toggle. I need to be in liquor mix. The instructions, if I was reading them, told me that. I'm going to toggle the transfer pump on, and what I was looking for is that this is the pressure in the white liquor line, and it should come up over 800 kilopascals. What it's doing is it's recirculating a little tiny bit back into the tank. I'm going to go to the graphic now so that you can see it, and you can see here the pressure's coming up, I hope. Okay, I've got to go downstairs and throttle that valve a little bit to get that pressure up a little bit higher. Okay, so we're going to charge water in. The pressure's a little bit low right now. I suspect there might be something not happy with that pump, but all we're doing is pumping it into a vessel that has got no pressure on it. It's sitting at 0 kPa. So what we're going to do is we're going to go to liquor charge, and in this group, what we're going to do is we're going to select water, which we've done, and what I'm going to do with this controller is I'm just going to put it on automatic. It's getting a remote set point from a Calcs block. So it's opening up the valve, and as much as it says it's white liquor, it's really water right now. And you can see that the flow over here on the right hand side is on both of these totalizers, but only this one is counting because we selected water. This one's in hold. And so what we've got to do is we've got to put in our water into there. And if I go back to previous display, you'll see I want to put in 13 kilos of water. Now, we built, and right now it's got 2.1 and climbing. We go back to this display here. There's a Calcs block in the background. And what it does is it looks to see what is the target value you're going to. And where are you? The target value we're going to is 13 kilos for round figures. So when we reach 12 kilos, 1 kilogram less than the target value, it will automatically change the set point on the flow controller from 4 kilograms a minute down to 1 kilogram a minute. Then, once we get within 300 grams, so that is 12.7 kilos in there, once we're within 300 grams, it now drops the set point down to 0.3 kilo or 300 grams per minute. And then when it finally hits the target value of the 13.0 whatever kilograms that we require, it's going to push the controller into track, and its track output is set to 0, so it will slam the valve closed. It's just like you filling your car with gas from the gas station. If you keep the pump on, that pump handle on full all the time, it's going to come out flying at you. Now they put automatic devices to sense back pressure and that kind of thing. But the point is that when you get close, you should slow down. And that's basically what this is going to do. So we minimize overshoot. Okay? Good. So it's just done it again, but we can see this on the water, but it's actually came from 4 down to 1 and from 1 down to 0.3. And we're at 12.9, we want 13.06. And so anytime now we should see a track flag come up on here. But it slowed right down. There it is. The track came on, the output went to 0. I'm immediately going to switch this from water to liquor. So I go toggle. And as soon as I did that, the water's trapped and did. This guy's gone back up to 4 kilograms a minute. He's opening up the valve, and we are now metering liquor in there. Well, you can clip off anyway. Okay, so the target is 25.9, where there, it just dropped. It dropped from 4 kilograms down to 1 kilogram. And we're supposed to be going to 25.9. So when we get within 300 gallons, under 25.6, you can see this is climbing slower. 25.6, and any second this guy should drop. There we are, down to 300 grams per minute, or 0.3 kilos. And then once we hit the 25.9, it's going to go to track and dry this out with the 0. And there it is. Okay? So now what I'm going to do is I'm going to put this guy back in manual. It doesn't open up. And I'm going to go back to my liquor mix group. And you can see this was the liquor tank, the white liquor storage tank, and I paused this guy. We started off at 183.59 liters of liquor, and we currently have 154.48 liters of liquor. So we have put in a fair amount of liquor. I'm going to shut off the white liquor transfer pump. I don't need him anymore, so I'm going to toggle him off. And if I go back to my previous display, you'll see that my pump is down, everything's down. I'm going to actually switch this back to water, just for safety reasons. So I'm going to toggle that on. And now, go back to previous display. You've got in the write-up, you guys have a form that you're supposed to fill in here. And we got to put in all these weights, which we're going to go through and get them all for you. I don't have a pencil. You have a pencil? Okay, we're gonna get all this data off the screen so that you guys can put it into your notes. First of all, the species. And this is on page 51 of your booklet. The species. This, by the way, is a hand-in, which means that you're going to have to take this document and PDF it and send it to Charles to prove that you actually did the lab. So the species is hemlock, okay? And in fact, I've got them on the screen right there, okay? The bone dry content was 40.89, which is right there. The green weight charge here can come from the chip charge, which was 31.252 kilos. The chip water weight, can't get that off of here, but we can get it fairly easily by going to Operator Calcs. The chip water weight will be your bone dry, okay, times the amount of moisture that's sitting in there. And or the other thing you can do is you can just take the green chip weight and subtract from that the bone dry weight, okay, which we calculated, and get the chip water weight. So you guys can do that. The liquor to wood ratio was 4.5 to 1. Okay, so that's the next one. Active alkali analysis of the liquor was sitting at 98.58. So that's the number that you would write in there. Then the white liquor SG was 1.113. And if I go back to my previous display, I think, yeah, it's still only showing as 1.11 there. The total liquid weight is the green, the chip water weight, the water that you added into their weight, and then the weight of the liquor. And that'll be the total liquid weight that's going in. White liquor charge. Okay, so on this sheet, and Charles, you can get back down here. On this sheet, I got two spaces. Actually, unfortunately, when I printed this, but yours should have another space there. So on the white liquor charge, the set point was 25.970, but the actual value we got was 26.123. So we overshot by a little bit. We overshot by 140 grams, which is more than normal. The water, on the other hand, our target was 13.062, and we got 13.28. So again, a bit of overshoot, but not much. But record the actual values sitting on the side here. Okay, so the next thing we're going to do is we're going to change screens. Because we got our liquor in there. We got our lid all bolted down. And what we want to do is we want to start up our circulation pump. And so, back here, make sure that I don't miss anything. So we got all that in. So high pressure water needs to be on. I'm looking at the booster pump right now and it's on. I can see a pressure gauge over the other side. And you saw us turn it on at the very beginning. So now it says from the liquor sidebar, liquor charge display is not already currently selected. Select the liquor recirculation pump. That is the pump on the bottom of the digester. There's two ways to get to it. One of them, you can just click on this and it'll take you to that page. And this is the liquor recirculation pump. So I'm going to start him. I heard him come on. And then I got a mag meter measuring. That chirping that you're hearing in the background downstairs is the dry seals on the digester, and they'll stop chirping after a little while with it running. Okay, we should be up over 30 liters a minute, or typically 35. It's running 33 right now, which doesn't upset me a lot. On your report, you're going to write in the liquor recirculation flow is sitting at, call it 34. It's climbing, bouncing up and down. That's a mag meter sitting in there, and we're measuring that flow. Next thing we want to do is take a look at the conductivity. What we got is we got an electrodeless conductivity meter sitting down there, and it's currently sitting there trapped. So what I want to do is I'm going to go down. Oh no, it's good. It's got liquor going through it. I opened the valves when I was down there. So right now, record the start liquor conductivity as 199,876 microsiemens per centimeter. That's there. When we're finished the cook, just as we're coming at the end of the cook, we're going to take another look at that number, and what you'll see is the conductivity has come down. The liquor has actually been consumed, it's been depleted, and it could typically be down at around 100,000, 90,000, depending upon how much liquor it took to dissolve the ligands that were in the liquid itself, in the chips itself. Okay, now, up on the top of that operations data page, steam supply. Right now it's at 1025. A little bit later I'm going to raise that pressure up just as we get going. But you could note down there 1035 or 1025. It's 1025 over here. He's running 1035 on the boiler, which is across the street. Steam consumption right now is 0. Now it should be 0. It may be 0 because we reached the totalizers, but I'm going to go to liquor here, which is, let me go back. This is the heater. The liquor is going to be pulled out of the digester through the pump, through the heater, and then back into the digester, and it's circulating continuously. These little dotted lines that I added to the graphic here is showing that the chips are actually there and the liquor gets sucked through those screens. So I'm trying to show what the screens look like before the ball down. All right. So steam consumption. We're going to go to the liquor heater group. And the liquor heater, I want to make sure this totalizer is clear. Now, because we rebooted the computer, we had some issues with the controller. These are all set, but normally you would go and you would toggle that. So this is going to tell us how much steam we actually use, the number of kilos of steam, and it's minimal. This is a steam flow meter measuring the steam flow with an orifice plate in kilograms per hour. The start time, when we actually apply steam, we'll record that time. The blow time was when we actually blow the digester. Impregnation ramp time will typically be 45 minutes, it might be a little bit longer. On target cooking temperature typically is 170. The amount of minutes that we were at 170 is recorded. The accumulated H factor. I got to come back and describe to you a little bit later what an H factor is. But for right now, it's got a number in it which it shouldn't have. So I'm going to go to Digester Control page. On the Digester Control page, there should be an H factor totalizer which should be showing nothing. Interesting. Why I had 23 on my page, I'm not sure. Anyway, it's been cleared. And typically we're going to cook to a 1600 H factor. That's described in the notes, but I will come back to it as we're progressing through the cook. Okay, and the recirculation flow you recorded. So we basically have got everything in order, and we're more or less ready to go. Okay, so the next thing we got to do is we've got to heat this digester up. And if you just throw the heat at it, what will happen is that the chips, and I think I've got samples of the chip here. The chip, sitting like that. The liquor's trying to get in there and mixed with the water and the lignans. If you were to cook a steak, and you want to cook your steak really well and keep it nice and juicy, the first thing you do is you sear it. You throw it on one side and you give it maximum heat, sear it, and flip it over, and that keeps all the juices in there. Well, that's not what I want to do with this chip. So it's important that I bring the temperature up on a slow and gradual ramp. In the mills, they typically run over 90 minutes. With this little digester, we can do it in 45. If we tried to do it in 30, the chip's actually sealed up, and we didn't get proper impregnation, and therefore we didn't get proper cooking. So we're going to go up over a 45-minute ramp. So we're going to go to the liquor heater page. And on this page, there's your steam pressure. There was our liquor steam, our steam flow to the liquor heater, the steam totalizer. The recirculation flow is at 34 kilos. Across the bottom are the temperature controls. Now, this is rather unique. You guys have all been through Cascade Control, and this is a form of Cascade Control, except that it's a double cascade. So in Cascade Control, you remember that you've got a slave and a master. This guy has got a slave, a master, and a supermaster. Now, back to the digester overview. What's happening is that during ramp-up phase, the liquor temperature is going to control the steam pressure. Just wiggle the lace. Okay, so you remember in Cascade Control, you would have a master, and then this is your slave. So we're using steam pressure to control the liquor heater. And that's very common. High degree of self-regulation with this slave pressure controller. What we're going to do is we're going to ramp this thing from room temperature, 24.4 degrees, up to 170 degrees C over 45 minutes. Once we've got up to the 170 degrees C, then the chip zone temperature down here inside the center of the digester will set point the liquor temperature, who will set point the steam pressure. So this is supermaster set pointing master, and master is set pointing slave. Okay. The reason for it is that you've got a high capacity and a small volume. Your house is a good example of that. When you're heating up your home, your furnace is a small supply, your house is a very large capacity. And you remember back from all the control stuff that you went through that the appropriate mode of control for a large capacity small supply is on off. You turn it on and you wait until it warms up and then you turn it off. Well, that would be pretty crude in terms of trying to get my chips not to sear, not to close up on me. So we had to have liquor temperature, but then once we get it up to temperature and we're at temperature, we want to control the temperature in the digester, hence the double cascade. But during ramp up, this guy is controlling that guy, this guy is tracking. When we get up to temperature, this guy track releases, he now drives his set point, he drives his set point. Okay? So, back to the liquor heater group. Slave, master, supermaster. So you guys have all figured out ISA symbology now. What does PIC stand for? Well, you can't answer the question right now, so I'll answer it for you. That's a pressure indicating controller. And what is TIC? Well, that's a temperature indicating controller. And this guy is a TIC, so that makes sense. Chip temperature, set points liquor temperature, set points steam pressure. So what the heck is a TKC? What is K? Well, it depends upon whether you're looking at SAMA or you're looking at ISA. ISA, K is time. In SAMA, K is gain. And so you need to realize that this is an ISA standard. And so it's temperature time controller. That's my ramp controller. Now right now he's sitting here running, and it's only because the computer rebooted, so I'm going to toggle that off. Then all I got to do is I kind of got to get things sort of set where it is. Right now our liquor temperature is running at about 24 degrees, so I'm going to put this block in manual, and I'm going to set the output to 24.7. See, it goes down, and it's now dropped the set point to 24.7. So this guy's getting a set point from this ramp controller. Then the next thing is that this guy is stuck here in manual right now, and I'm going to move him down to the same temperature. So I'm going to draw, and you watch, the output of this is actually going into the ramp, and then we're going through the ramp and out. Right now the ramp is in manual, so nothing's passing through. So I'm going to set that at 24.7 as well. Oops, I'm selected to there. So 24.7. And you'll see this guy change and that guy change. I hope they did. Okay, and there's our target. That's what we're going to. So, we're basically ready to go, except that, how do we get this ramp? Well, we're trying to climb up to 170 degrees. So you get your calculator out. Get rid of converter. We're going to 170, so 170 minus, we're at 24.7. We've got to go up 145 degrees. And I want to do it in 45 minutes. So I divide that by 45. That means I got to climb up at 3.2288888 degrees per minute. So, right now it's up ramp is set for 3.38, and I want to get to 3.22. So I'm going to go to detail on this block, right there, and this is my ramp up. And my up rate was set at 3.38. I'm going to move to 3.23. And so now my up rate is 3.23. If I go back to previous display, I'm going to go up at 3.23 degrees per minute. Okay? So now the next thing to do is to, I got to open up the steam valve. I'm still in manual. Actually, I'm going to put this guy over here in automatic. When I do, you're going to watch, he's going to go to track. So when I go to auto, he just went to track. Why? Because we're not at 170 degrees. When we get to 170 degrees, the track will get released. Otherwise, his output is going to be tracking what we're doing over here. That way, when we switch over, no bump. It's bumpless transfer. So the output is tracking what's going on in this ramp function. All right, so the next thing we got to do is I got to put some steam in here, and I see my steam valve is open too much. The hand valves are closed right now. I heard the steam valve back off. I'm going to take this output and move it down to 0. Okay, so, and you'll also notice with the phosphorus system, it's kind of neat in that you can have your output on a controller, on a PID controller, in any units you want. For example, the slave controller, his output is 0 to 100%. Why? Because he's driving a valve. But the master's output is in kilopascals. Why? Because he's raising and lowering the set point of the pressure controller in kPa. So he's actually in the engineering units, which is kind of cool. So I'm going to go and I'm going to open up the steam valve, and I'm going to actually manually open it right here to about 30%. And I'm going to go walk over the other side with my gloves, and I'm going to open up the hand valve and start drawing steam. Okay, so this was the digester. That's the liquor heater. So the liquor's coming out underneath the floor, going through the pump and coming back up on a single pass through that heat exchanger, comes up out of there, through here, down through here, through there, and then goes into the digester. So this is the liquor heater. On the liquor heater, there is a vent valve sitting on the side of this thing, which we're going to bleed the air out. So I'm going to open up the block valve around the side over here. Is my control valve. And this valve is right now 30% open. I'm going to open up this hand valve. The bypass is closed. And I can hear gurgling happening over the other side over there. So we're going to go back and watch that. Now I push the air out. See it puffing? Got to get all the air out of that heat exchanger. I'm going to go back. Actually, yeah, I'm going to go back to the panel and open the valve up a little bit. I'll be right back. Okay, push your steam out nicely. Got to close this off so no air gets back in. So we filled the steam chest with steam, not air. Okay. So this guy is a bit rocky to start at the very beginning, because even that little tiny bit of steam that we threw in there pulled the temperature up on that liquor. So it doesn't require very much to start with. So I'm going to move this guy into run mode, which means this guy needs to go to auto. So he's an auto and remote. The master is going to go to auto, and actually I'm going to cheat. What I'll do, I'm going to take this output on here and move it up to 33. It'll help, but it won't bump quite so bad. Oops, wrong one. Yep, there it is. So everybody's tracking, everybody's good, and I'm going to hit the run button. Got to go to auto on this master. And so now, if you look, got to put this guy on auto too. Now he'll start ramping. You can see the output ramping, 33.2, 33.3, 33.4, and that's changing the set point over here. So it's going to ramp up over 45 minutes. and hopefully get up to temperature. This guy is stuck in track, so everybody's in auto. This is auto and track until we hit 170. This guy is in auto and he's in run, and he's controlling our ramp. He's ramping this guy's set point, and it's a moving goalpost. What's going to happen? This thing's going to put steam on it, and it's going to be way too much, and it's just because you're starting at the very bottom, and it'll settle itself out once we get going. I'm going to go to a ramp trend for a second, and here we are right here. This is us just starting, okay? And you'll see in a little while this ramping. So the cyan color in here is the chip temperature. This is inside the digester. This is the liquor temperature. So you can see the liquor temperature is higher than the chip temperature, which should make sense. The steam supply is right now sitting at 1027. I'm going to go get the engineer in a few minutes to start raising that up. And our liquor heater steam pressure is right now running at 20 kilopascals. If I go back to previous display, you should see that it's got that valve. Why is that valve so far open? I'm wondering if he's got valves closed downstairs. I gotta check. Okay, we had some fun going on. The safety valve over in the steam plant was blowing, so we dropped our pressure back down a bit. But if I look at the trend, which I think you can see over there, this was the mess that was over in the steam plant. But what I wanted you to see is, you see this nice ramp? That's that ramp that we're running up. And if I just click back to the liquor heater, right now its output is set pointed at, on the ramp, 131. Where we're going to get into trouble is we're going to run out of time, because the steam pressure is lower now. I dropped it back down to 1035, so it's not lifting the safety. The safety is weak, and it was supposed to have been changed this summer, but it didn't get done. COVID caused a lot of things to not get done. Anyway, bottom line is that this timer is going to run out of time before we ever get up to the 170, and we'll just have to grin and bear it. Back to the graph, you can see the steam pressure is going up, and that's the steam pressure over here. Eventually we are going to get to a point in time where we just don't have any more steam, and we're kind of waiting for the temperature to inch its way up. And we got another 40 degrees to go. We're at 130 now, we want to go to 170. At any rate, it is what it is. Now, back to the overview of the digester. You can see that the liquor's coming in at 132.8. It's spraying into the digester at 131.3. It's dribbling down through the chip, so it's lost, or it's given up a little bit of heat. 131.6. Earlier, while I was over in the steam plant, Charles vented using this vent valve to get the NCGs. So the temperature in this upper area would have been lower, because it had air trapped in there, and all the non-condensable gases that are being given off by the chips themselves. In a more traditional, much larger digester, this would be continually being vented off. But this thing is so small that we get very little NCGs coming off. But the NCGs, non-condensable gases, which are turpentines, that kind of stuff, come down through here and go into the vent hood, which is this line here. And there's a water shower. I'm just going to flip it on for a second. Vent shower. All along, back to display. And you can see that we animated a little bit, so you can see some water going in there. I'm going to turn it back off again. We don't need it. Toggle it. Back to previous display, the valve is off, and we're away and laughing. So, what would have happened is this temperature would have come up, and there is in fact a relation control stuck in here, just right here. No, wait a minute, next page down, maybe. That's the dome temperature digester relief control. So this is a relation control looking at temperature pressure relation, and if you went to remote set point on it, it would actually be looking for what pressure should it be running at to get at the temperature that's looking for. And we, as I say, it's so small we can't really run it, so you get the basic idea that the control is there. But that's back in all your control systems notes. There was a thing on relation control, and there was also an example on a batch digester doing relief control. It could be either pressure, or temperature, temperature, pressure, or temperature. And I probably could have gone with a temperature by simply looking at what temperature that was at and what temperature this is at, and knowing that I would have a very small difference between the two once all the gases have gone out of there. So could have gone that route. All right. So right now we're warming it up. How do we know when it's cooked? There's a thing called H factor, and it's actually in your notes on page 52 of the book. And you can read that through as well as I can read that through. But this was developed by a gentleman by the name of Baroom in 1930s, and he postulated mathematically how well it would cook. It goes up with temperature. And pulping, the actual manufacture, the production of pulp is actually a natural process. If a tree falls over on the forest floor, in 10 years, it's going to look like that. It's going to be a bunch of pulp. It's just going to be mush. So what we do is we speed it up. We increase the temperature. Anytime you want to cook something, you raise the temperature. And then we also applied some chemicals, sodium hydroxide, sodium sulfide. The sulfide goes in and dissolves the lignins that are holding that piece of wood together. I had a chip in my hand a while back. Put it back in the bag. And so the sulfide and the caustic go in there, and the caustic needs to be there. We're up around 12.5 pH in there, 13 pH. And the sulfide, sodium sulfide, impregnates and takes the lignins, the glue that is literally holding this chip together, and dissolves it. And the white liquor that we started with, that looked like this, nice white liquor, kind of got a little bit of a yellowish hue to it, and that yellow is the sulfur. That white liquor will become black liquor. And this black liquor is in this bottle. I don't know whether, Charles, you can get a picture of the top, but you can see it almost looks like chocolate milk or something. Don't drink it. It's bad for you. It's real bad for you. I think I showed you guys the other day the lack of hair that I've got on my skin. That was not hot black liquor. That was this white liquor that got onto there. Anyway, so the blackness of it, black color of it, is the actual lignins itself, the glue that we're taking into solution with that black liquor. And we need to know when have we removed all those lignins. So to do that, Baroom came up with this formula, and it calculates this thing called an H factor. And there's a table in here. This table is the TAPI table, and I go through this when we're going to go through the PowerPoint. But at 100 degrees C, it's one H factor, one count. And that's basically, it's a rate, so it's a count per hour. You're getting 1 count per hour. Whereas if I elevate the temperature to 160, I get 397 counts per hour. Or if I elevate it to 170, it's 921. If I elevate it to 180, it's at 2056. It's not linear. It's following a Neperian or natural log curve. And so the formula says the cooking rate will be equal to the ln, the natural log of 43.2 minus 16,113 divided by the temperature in Kelvin. Now we gotta go from Celsius to Kelvin because we're measuring in Kelvin. So, or measuring in Celsius. So I'm going to go to this H factor while we're going through this cooking thing, ramping, and digester control. So this is the H factor totalizer, and currently the temperature in the chip zone temperature right there is sitting at 151.7. So if I look at my table, 151.7 would be about, well, it's 151 is 180 counts, and 152 is 197 counts, and we're sitting at 197 counts, and we're sitting at 152.48. The table is not absolutely perfect. This computer is using Faroum's formula and calculating it. And if you were to take a calculator and go through the calculation, you discover that this table isn't all that perfect. Well, this table was done with a 3-inch slide rule. Okay, so give the guy a break. It's actually pretty darn good. So, I want to dig into this thing a little bit, so I'm going to go to the Totalizer, and I'm going to go to block detail, so that I've got my Totalizer up. And the question is, where's this coming from? Well, this is AQ. Q means total in ISA. So what I'm going to do is I'm going to look for this measurement, and I'm going to go down here to source. And the source of that measurement is AC, Analytical Calculator. This is Analytical Totalizer. This is the Analytical Calculator, and it's a calc block. So that's the source path. I'm going to click on that. It takes me right to the block. The block is not a block that the operator would normally see. There's our temperature coming in from our chips at 155.88, which if you look up in there, it's 155. And it's calculating an H factor at, now it's at 156 and climbing. H factor, according to the table, should have been between 281 and 306, and yeah, we're between 281 and 306. How did it do that? Well, this thing is a neat calculator. You pick up your calculator and you look at your calculator, you might have some memories. Well, this little puppy has got 24 memories in it. It can bring in integer values. It can bring in Boolean values. Up to 8 or 16 inputs and 8 outputs. And then, of course, what it's looking at is the real I/O. And we're only using one point of it. The question begs, how does it do it? Well, this is the steps of the calculation. Now, this is, if you look at this, it's a funny-looking language. This is reverse Polish notation. For any of you that were around when calculators first came out, the Hewlett-Packard calculators, you would clear the stack like you do with your calculator now. You hit the clear stack, and then you would input a value, and then you would enter another value, and then you would tell it what math function to perform, and the result would pop up on the top of the stack. That's how a computer chip actually works. The calculator that you've got has got an interpreter in it to interpret, to go to the chip. So this is a very efficient method of programming. And so here we're going to input real input number 1. Well, that's the temperature. And then we're going to load the accumulator with a value stored in memory 4. So let's go look at memory 4. Memory 4 has got 273.15. Now I wonder what that does. 273.15. Oh yeah, that's the conversion between Kelvin and Celsius. So we loaded that into the accumulator, and we add it. So we've taken the temperature in Celsius and added 273.15, and we store that in memory 5, which if I go to my memories, memory 5, there is the temperature in Kelvin. So the temperature was coming in at 159, add 273.15 to it, you got 433.51. Back to steps. That was the first part. And in fact, if you looked at the formula here, all I was trying to do was figure out what T was. So in fact, that's T stored in memory 5. Clear the stack, load the accumulator with memory 3. What's memory 3? Well, memory 3 is 16,113. And you go back to his formula, that's the 16,113. And in fact, if you went through the original documents, you would see it says 16.113. And that's because the Europeans do not discriminate between a comma and a decimal point. But in fact, it means 16,000, and that's what it is. So that's our 16,000. Now what we're going to do is we're going to take that, put that in there, load it in this value, our degrees K, that we have in memory 5, and do a divide. That's what the formula said to do. And then I stored that in memory 6. So just a temporary memory. It's moving around all over the place. I stored that. It's at 37 right now. Then the next thing is, and I might as well point it out, memory 2 has got 43.2 part of the formula in it. So if I go back to steps, I cleared the stack off, load in memory 2, which was the 43.2, load in memory 6, which was this part over here, the 16,113 divided by the temperature in Kelvin, and subtract them. That's what we're supposed to do, and store that in memory 7. So that's all this stuff. And so in memory 7, it's 6.27. And then you're going to raise that to the Imperial log, e to the x on your calculator key, and that will come out currently at 540.69. So we've actually done the formula, and we're doing it every second. Okay. Let me close the overlays. Let me go back to previous display, and let me go back to my overview. So right now we've counted up 52 counts. We would have been here for 10 years if we left it at room temperature, but we've sped it up. And so currently we have accumulated 54 counts, now 55, 56, out of 1,600. So we've got a ways to go. You can see the liquor's coming in at 164. I see another problem. 163 in here. It's 164 in there. It's coming back out at 161. So we're taking heat out of it, but not very fast. Now, over to my trend over here. There's a problem. There's our steam pressure, and you can see now that my valve, my pressure has come up constant. I'm still raising in temperature, but my pressure is holding dead constant. And that's because that's all the steam I'm getting from the steam plant, because the steam plant's got problems right now. If I go to my liquor heater, you'll see my steam valve's wide open. There's no more. Okay, and it keeps going in and out of hold, because every time these guys hit the top end, this thing just goes into a hold mode. But there's no more I can do with this thing other than throw this guy on manual and go up to 100, but it's at 100, I think. Let's go to detail. Oh, I got a high limit of 99. I'll give it another percent. There, high limit is now 100. It's not going to do much for us. So we're kind of stuck until we get to 170. I know we're not a long, long ways away. We're at 165.7, so we got 4.3 degrees to go. Okay, we're almost at the top of our ramp. As we discussed, we had some problems with the steam plant. I've got that settled back down again. Currently, the chip zone temperature is sitting at 169.63. Liquor temperature is sitting at 169.88. And we need to get to 170 for the track to get released. And the moment the track gets released, this guy will be set pointing that guy, who will be set pointing that guy. And you'll actually, may hear, but you'll see the steam valve will throttle back. It won't be up as high as it is. We're getting close. It's 0.86. It just released. It's off this one here. So the track is now gone. This guy is now set pointing that guy, which is actually passing right through. I'm going to take this and turn it off. And we're there. So we're now sitting at 170 degrees C, which is our cooking temperature, and you can hear now that I just heard that steam valve starting to throttle back, and you can see it starting to come back now. So it takes a lot of extra inertia to raise the temperature of all of the metal, the chips, the liquor. You've got all that. Once you've got it up to temperature, now you're just going to hold, so it'll back right down. It doesn't shut off, but it's just going to basically maintain it. Back to the screen for a second. So far, through all of this, we've used up 37 kilograms of steam. You can almost bring it over here in a bucket. There's not much we're using, and it's backed right down to a steam flow of about 21 pounds an hour, 21 kilograms an hour, which is next to nothing. But that's where we're going to sit now for the next while. So the one remaining thing we need to figure out, and I don't know whether we got enough time left on this guy. Let's go to digester overview. Once we've reached 1600 H factor, we then need to shut the steam off and blow this digester. So it took 53.2 minutes to ramp up. That's because we didn't get to as high a temperature as we wanted to. We're now, the minute that that ramp ended, we started cook time counting, and so we're counting how long we're at cook. And we're going to be at cook for about 90 minutes or so, possible. Okay. So currently we are at 520 counts and rising on our H factor. We now use 42.5 kilograms of steam. It took us 53 minutes to ramp up to the 170. We've been on cook time now for 22 minutes. So it would be nice to know, when is this thing going to blow? And in here I've got a time to blow calculation. All that time to blow calculation is doing is that it's simply taking the target that we want to go to, subtracting from that the accumulated H factor. So for, let's just, because it's moving, let's for round figures say that it was 550 counts in there. That means that we would have 1,050 counts left to go, or 1,150 counts left to go. What we can do is that we then can take and divide that by the current H factor. So if I go to the digester control group, you'll see that currently we are counting up by 1,034.79 counts per hour. We've accumulated 537 counts. The reason it's running a little bit faster right now is I tweak the temperature up a degree, and in doing so the H factor counts per hour is going to increase. I'm trying to get this thing down a little bit quicker. The disadvantage of doing that is that when the digester blows, and I'll talk more about the digester blowing on the next part of the video, but when the digester blows, if the chips are really hot, when they blow apart, it'll tear the fiber. So the chip itself still looks like a chip like that inside the digester, even though all the ligands are dissolved. When you open the blow valve, the pressure drops, and the water that's inside here flashes into steam, because inside that digester we're running at digester pressure of 700 kPa right now, and that when we drop the pressure down to zero, the water inside here is going to flash, and it literally blows the chip apart. Hence, if I go back to digester overview, this is called the blow valve. So the chips will still be chips up here, 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 and as they go down through here, they literally expand and blow into pieces. Okay? Out of time?
You done? You can continue.
Got a little bit more. Did I?
3% battery life.
I don't think we're okay, because we showed the HVAC. The only thing we haven't done, and let me just finish off.
You can continue.
Okay.
I'll just edit it.
So, knowing that the H factor was running at 1,000 counts per hour, if we had, let's say for argument's sake, we had 1,000 to go. If we had 1,000 counts to go, then at 1,000 counts per hour, it would take 1 hour of cooking. And that's how it would calculate that. Oh, look at that. Look at how close we are. 61 minutes. And so it's constantly, look, this is almost at 1600. This is 1580. And the minute that hits 600, it would be 1000. Okay, and 1,000 at 1,000 counts per hour of current H factor would basically be 1 hour, and then you multiply that by 16, you've got 60 minutes. Okay, and that's how we calculate the time to blow. Now, we take a sample of the liquor about 10 minutes before the blow. This is a cooling jacket sampler, so the liquor is coming down through here, getting cooled, and goes down into our beaker that we pick it up in. We brought it back over and we put it in a graduate. Then we use a hydrometer. And you'll see the scale goes from 0 up to 12. And that is in degrees Beaumet heavy. Okay. So, same as you did when you were looking at the evaporators or the distillation column, any one of them we've got the glycol in, put the hydrometer in. With the hydrometer, you need to have a thermometer, because this thing is only accurately reading Beaumet when you're at 60 degrees Fahrenheit. Okay, starting in. So, hydrometer is in there and it's reading around, gee, that's low. It's about 6.5, but it's at elevated temperature, so we'll have to do a fair amount of temperature correction. This temperature is in Fahrenheit. It's up at 110 now, climbing pretty fast. We're now at 130. Remember 5 time constants for this thing to flatten itself out. We're at 150. That's F. It's 155. Looks like it's leveling off. We're going to call it 160. And the Beaumet is that. Coming around. Still coming around 6.6 at 160. Record that down on our sheet. So it was at 160F, and we said 6.6. We'll figure all those corrections out after we get the blow done. Okay, before we actually blow the digester, I'm going to go back to digester overview. The blow tank that we're going to blow into, we need to put in 450 liters of warm water. So I'm going to open up this solenoid. Hello. And warm water solenoid. Sorry, that's my lunch. Typical operator. And toggle. It should have turned on. And I think the handbells are closed. Okay. So we're coming to the end of our cook. We decided to let it go to 1800, so we're at 1798 right now. So the next step that we're going to do is to shut the steam off. So I'm going to go to the liquor heater group. In the liquor heater group, I'm going to put the chip temperature control on manual, set its output to 0. So that's the super master. And then I'm going to go to the master and put him on manual. and set his output to 0. And then the pressure control has already gone to 0, so I'm just going to throw them on manual. So we basically have shut the steam off. I'm going to go isolate the steam valve. Yeah. So we shut off the manual steam valve over there. Now what I got to do is I got to shut off the circulation. So I'm going to take the recirculation pump and toggle it off, and the flow will go down, and it'll get air in there or vapor in there, and this thing is going to go into alarm in a few seconds. It'll turn red. Not a big deal. What we should record now is the accumulated heat factor, which is 1840, 46, yeah, just call it 1850. It's hot in there, so it continues to run. So anyway, we've shut this guy down. Next thing we need to do is to turn on the vent shower, because it's going to be smelly. And so the vent shower goes on. Toggle. So the vent shower is on. That valve's closed. Blow valve is still closed. No more circulation going through. The conductivity right now is at 71,875. 71,875. And you remember we started up way over 199,000. So we've consumed a lot of the chemicals out of the liquor. So now the next step is to open the blow valve. Now, before I push this valve open, which is up here, I want to look at the back of the lab, and I don't know, Charles, whether you can see the vent. See the vent up there, the silver vent? That's what I want you to focus on while I hit that valve. On when you're ready. Ready? Okay. Now, over here, inside previous display, you can see that the pressure has gone to 0. Okay, remember it was sitting up at 800 kPa, and so those chips literally exploded going through there. I'm going to turn off the vent shower because I don't want to put a bunch of extra water in there. So I'll close that. And the blow valve, we're going to close it, because what we're going to do is we're going to put water in the digester and then circulate it to flush the digester once we take the lid off. To ensure that there is no pressure in the digester, I'm going to the control group, and the relief control, I'm going to open that valve up to 100%. So the little relief valve that's sitting on the top will be wide open. The picture that we have on here shows us there was 2 kPa in there, now it's going down. So once I closed the valve, there was still heat in there, and it was creating some pressure. So now I've got that vent valve open, and it's actually being sucked up to the roof. So now we can take the lid off the top of the digester. Okay, taking the lid off, you can see that it's moved off to one side. And I'm going to look in here. Oops, it didn't cook all that clean. It didn't get a clean blow. It kind of blew out the center. As you can see all the black liquor around the edges. We're going to actually wash this stuff out of here with water. So, Charles, I need the hose, please. So I'm washing the liquor off. You can see there's still some liquor on this side here. And look when the water hits that liquor. Just peels it right off of there. Okay, now comes the fun part. I need more pressure. Charles is going to wash this down. Okay, so we washed the extra stock that was stuck on the side of the digester out. Take a look down in there, and the blow valve is currently open. Okay, and I am going to go, you're going to hold that, and I'm going to go close it. You'll be able to see it close. Okay, so we're all closed up, and now you can see this shiny ball valve, and you can see the screens just up above it. Okay, good. So now, what we're doing is we're circulating the liquor out of the lines and back into the digester. You can see the actual flow pattern. You can see that it was quite dark to start with. Before it's very brown. Now it's starting to get lighter brown. And when it's about just starting to show color, it's around 400 microsiemens. And then, of course, when it was in the digester, running as black liquor, it was up at 30 millisiemens. That is 30,000 microsiemens. Significant difference. You can see it's come back black again. You can see that the upper jets are centered towards the center. The lower jets are making another ring around the inside. Then we're going to shut this off, dump it, then we're going to fill back up with water and flush it once more. Okay, we're in the second part of this lab. We're going to do a wash, ground stock wash today. And to do it properly, we actually have to take a consistency check of the stock before we put it in the washer, and then do another consistency check after it's gone through the washer to determine thickening ratio. And there's a number of other things. So I'm going to take one sample. Now I've got one in here right now, which is sort of dried out. And I'm going to disconnect the vacuum. And this is I'm going to average. I'm going to do two of them. So this particular one, that slurry that I poured on here, was 301 grams. The filter paper itself was 257 grams. I'm sort of making notes down of it. And this is my sample number one. So where he's going is over here to the drying oven, which I hope is on. Yeah, it's slowly coming in. Now, we're going to do a second sample. And so to do that, I need to weigh the weight of the filter paper itself. So we'll tear this guy out. Filter paper weight is 245 grams. I'm going to make a note of that. If I had a pencil, I would write it on here, but writing it in ink, water goes through it and it all smears. So what did I say? 248. So that's 248 grams is what this weighs. And I'm going to put this filter paper, whoops, number side down in there, and I'll turn the vacuum back on. Actually, bear with me for a second. This is getting kind of full, so I'll dump this. That stuff I'm dumping, by the way, is black liquor. It's not as concentrated as it was coming out of the digester. Okay, so I've got a beaker here. I'm going to tear the beaker out, so the weight of the beaker is gone. I've got a sample that I took out of the number 3 stock tank previously. So what I'm going to do is I'm going to kind of mix that up a little bit and get an average sample. And it turns out to be 321.24 grams. 221.24. Now we'll pour that into Bruckner funnel, and now I can add all the water I want to here because we're eventually going to dry all the water out. So typically add a little bit of water and get the bits off the edges. Smooth it out a little bit. Okay, and then wait for that to filter its way out. So here's the stock that came out of the blow tank and into number 3 stock tank, and it kind of floats to the surface, and so you can see just a pad there. I'm actually going to turn the agitator on, and you'll see that pad start to move and then break up, and then everything has gone into suspension. I want to mix it for just a moment before I take my consistency samples, and then I'll take the consistencies or take a sample out. And what I've got to get is I've got to get the amount of dissolved solids that's sitting in that liquor. Okay, that's good. Okay, we're ready to start our brown stock washing. A few moments ago, we actually pulled some consistency samples from the number 3 unwashed stock tank. We also took some dissolved some of the liquor out of there with no fiber in it, and we're testing for the dissolved solids that are in there to start with. So we'll sort of have it before the wash and after the wash, so we can figure out how efficient this little washer is. So over here on the operating screen, got 2 things going. I've got washer overview sitting over here, and so I'll just describe this process a little bit to start with. What we're going to do is we've got some stock sitting in number 3 stock tank right now. There's about 1,000 liters in there, and I'm guessing that it's around 1% consistency, but when we get the samples back we'll know for sure exactly what it was. We're going to run number 1 stock pump and circulate back into this tank, continuously circulating around, and then we're going to take a slip stream off and run it into the washer vat. In the washer vat, the stock will form a level probably about where my cursor is, somewhere around there. Then we are going to pull vacuum. We're going to put on some high pressure water, and through a venturi, which is downstairs, we'll pull a vacuum on this vacuum receiver that's located up at the roof of the building. We've then got 2 valves on here, one air to open, one air to close, so that we can open this one and draw vacuum, or we can bleed air back in there, so at which point we're able to then control the vacuum, the drum vacuum. So we're going to pull vacuum in the center of this drum, and my drawing actually shows 4 quadrants in there. In fact, it's 3 segments, but it's just the way I drew it. What's going to happen is that we're going to pull vacuum, and the stock that's sitting in here is going to get pulled up to a wire on that drum, and the drum is rotating around, it's rotating counterclockwise, so the drum will come up to about here, and at this point it's going to suck the sheet on, then it's going to suck air through and suck the liquor into the center of this drum, and the liquor will end up going out into this separator. Then we're going to go up a little further. We're going to spray water down, 3 jets of water, and we'll be actually washing water right through the stock itself. Then the stock is going to get lifted off and go down this slide and end up in number 2 stock tank. To help it, so that the stock doesn't get caught underneath this blade, this is called a doctor blade where the pointer is right now, we're going to actually take and jet some air. We're going to put about 10-15 kilopascals air pressure up underneath there to help lift that sheet off. When we're washing, we want to wash with warm water. And so we've got some warm water coming in. We've also got some cold water so that we can control the temperature, because right now you can see the temperature is quite high. and I suspect that there's a failure with this transmitter. We would have had people in here calibrating all this stuff, but we weren't able to do that. And so that I think is going to create a problem for us. We'll run, but we're going to assume by my fingers touching the water what the temperature is. But typically I want to get to 50 degrees C. The water coming in here is around 60, 65, so that's what makes me think that that number is not correct. Okay, so the wash stock will end up in this tank. When the sheet is coming off, we'll have to take samples of that and then squeeze the liquid out of it to see how much dissolved solids is left in there. And that's going to tell us what the washing efficiency is. That is, there's a certain amount of dissolved solids in here, probably around 8%, 9%. When it was in the blow tank, it was at, or in the digester, it was at 14.5, but we diluted that down with a fair amount of water. So again, this is going to be down in the 8, 9%, I'm guessing, solids. And then coming out of here, it should be very fractional in terms of dissolved solids left in the actual fiber itself. Then what happens is that the water that comes into here, the filtrate, proper term, the filtrate that is sucked out of here goes into a filtrate separator. In the separator, we're going to pump out through this pump and control valve the filtrate. And when you see this running, this stuff is black. You can see that it's definitely taking the liquor out of the fiber itself. And we're going to control that level by controlling this valve. And that's pretty critical to control that. And what it is, we're maintaining the level just below where this connection comes in, so that it's free run for the filtrate to get in there and then get pumped back out. The filtrate will go into a filtrate tank. If this was a pulp mill, we would be shipping that weak filtrate over to our evaporators, where we would evaporate it, take the water out, concentrate the liquor, and then put it into a boiler, recovery boiler, burn off of the lignans and the chemicals that are in there, the sodium hydroxide, sodium sulfide, would actually become smelt in the bottom of the boiler. We tap that off, put it back over to recast, and then rejuvenate that liquor. So this is our little tiny baby brown stock washer, and the stock actually comes in to the bottom into this vat through that line down there. And down in the vat, I've got air diffusers stuck down in there. We're up in my laser. This is the drum. I'm going to turn it on, and so it's rotating. Okay. Vacuum will be drawn out here, and so fortunately I don't have my laser controls. That tank up at the very top up there, that tank is where the vacuum is sucked. And that line off the right-hand side comes down through here, through this valve and this valve. So this valve is pulling vacuum, this valve is bleeding air in. And we're going to maintain a pressure, a constant pressure of about 10 kPa, somewhere in that vicinity. This is the separator, and right now the separator is full of water. So we'll end up pulling that water out. The vacuum line comes off here, through here, goes down this gray pipe, all the way down there, and goes back over to the separator. So if I go over to the separator, gray line is coming right in there. And you can see it's coming in tangentially, so the liquid will spin around. And we're going to maintain the level at a point just below where that connection comes in. So this transmitter back here is actually measuring the level. No, that one's measuring the pressure, and this one down here is measuring the level. Just run it back. Okay. Water. We need water for the jets. That comes from here. And there's total warm water coming up from a whole bunch of valves, and maybe take a shot of this down here, this mess. But there's a number of valves. There's 3 control valves, a whole bunch of IMP transducers, and pressure transmitters down here. We're actually measuring the vacuum, etc. So the warm water, once we've blended it, goes up into here. I'm going to open this guy up. Okay, and then that water goes through a rotometer, not that we use it, and then through and to the jets. So what we're going to do now is we're going to go to the controls, and we'll start opening up to feed water in here and get the whole washer running before we actually put any stock in there. Okay, back to the screen. Okay. I just want to get something else on the screen. So what we're going to do is we're going to go to washer control. That's this group here. And we've got a number of things that we can set up. One of them is the vacuum. And if I take this on manual and put that valve to 100%, you hear the valve move, and right now it's this indicator is not quite right on there. The valve is actually closed. When I open it up, you'll actually see vacuum starting to get sucked on here. It'll start sucking air through. Okay? So I'm going to open it up to 100%. Or to, I'm sorry, take it down to 0%. And it's trying to pull vacuum, but it can't because of the fact we're just sucking air right through that screen. We won't see any vacuum on here until such time as we actually have a sheet form. So I'm going to put this guy on automatic. And he's all upset because the measurement is out of range. Okay, we'll just leave him for now. The next one is the sheet liftoff pressure. I'm going to open that up to about 20%. I can hear the air behind me and the pressure's gone way up. I'm going to bring it down a bit. The button I'm pushing right now are 1% increments. Those are 5% increments. Got to get fairly close to set point before I put it on auto. Otherwise it'll get itself into a cycle. Okay, next thing we got is we got a filtrate that's separator which is full of filtrate. So I need to turn on the filtrate separator pump, and I go back over here to pumps. The filtrate pump is that guy, which should be a manual. When the computer gets rebooted, everything goes to automatic for all these kind of blocks, and I need to have them in manual so that I can manually control them. Okay, filtrate pump is running. And if I open the valve up, not moving. can hear the filtrate going into the tank behind you. Okay, now what we're going to do is I put that on automatic. The filtrate tank will start to fill up, but I've got the valve wide open so it'll drain away. Next thing is to put some water in. So I'm going to start off with warm water, and I'm going to put that up to get a flow. And I want to be running at about, I think I'm supposed to be at 15. It's a bit high. 7. So I'm going to set that set point to 7 liters a minute. And it's pretty close, so I'm going to put it on auto. So this is hot water being administered right now. Now over on this other graph, you can actually see it's at 6.9 liters a minute. There's no cold water going in. It's going into the shower, and it's showering out. Our level is at 8.7 centimeters in the separator. Pump is on, and we're basically pumping around. I'm going to go over now and look at the water. You can see that the water is fanning out, and it's hot. It's fanning out, and sort of in 3 sections there, a little bit less on each one. And what that'll do is it'll wet the surface, and then the vacuum will suck the liquor and the water through the mat. And if you come to the side, I don't know whether this will pick up on your camera or not, but I can actually see the liquid coming out through there now. And if you look down into here, there's a little bit of liquid in there. Probably put a light on. And then come back around to the separator. And you'll see now that the level is down here and the inlet is up there. So we're coming in above it. Okay? Good. Okay. Good? So this you recognize is a pressure indicating controller, and a pressure indicating controller, and a level indicating controller, and a level indicating controller, flow indicating controller, temperature indicating controller, another flow indicating controller. This is the cold water flow. This, FFIC. Instead of being 3 letters, there are 4, which means one of them is a modifier. And that second F means it's a ratio. It's a flow ratio indicating controller. A ratio is nothing more than a multiplier. So it's looking at this flow, okay, that this is our warm water flow, and if this guy was in automatic, which he is, he would be setting a set point out of 0.038, so it's going to multiply that by 0.038. I'm going to take the ratio, which is coming from the temperature controller, and I'm going to change that number to a 1, so you can see what's going on. So now what would happen is that you would be multiplying that flow by 1 and set pointing that flow. Okay? And if I change that ratio down to 0.5, you would now see that 7.5 or 7 gallons a minute or liters a minute multiplied by a half is 3.5 liters a minute, which is the set point for the cold water flow. I know from experience that this thing typically runs at around 0.25. So I'm going to set it down there. And, oops, I thought it was 0.25. I gotta pick it. Oh, I gotta pick it first. And now 7 liters a minute times 25% is 1.74 or 75 liters a minute, which is a set point for the cold water. Our temperature is haywire. I know it is, but so long as I keep this on manual, basically it will control the ratio. This is what is known as a part to total ratio. So if we go look at the main graphic over here, you can see right now that the flow is all warm water. This is not measuring the warm water flow, it's measuring the total flow. So now if I go back and I take my cold water and I open that valve up quite a bit, it's a very small valve. And so now you've got 2.6 liters of cold being mixed with however much warm you need to get to 7 liters. Part to total. The water temperature, as much as it's still indicating 102, has probably come down a fair amount. Okay, we're going to start up our stock now. We've got this little agitator running, but we're going to run stock and bring it around through here. I made sure that valve's closed, this valve is open. And then what we're going to do is we'll start to slip string some of it off of here into this washer bath. As it fills up, the stock should then attach to the screen on the drum and come rolling across and basically come out this way. It's somewhat manual. We've got a lot of playing around to do and trying to get the sheet on the wire itself. Understand that this little guy that you just looked at is a model compared to the real. The real machines are up to 10 meters long and probably about 3 meters in diameter. So they're significantly larger. We were told at the very beginning that this little demonstrator would never work, but it does work if you play with it a lot. Okay, so we're going to get up here and try it. So, stock pump. Let's start from number 1 stock. Okay, let's go look. So the stock, the number 1 pump is being drawn from the bottom of this tank and recirculating back in. And then what we're going to do is that there's going to be a line coming off the ear which goes around and out the back. It comes through here and through that valve there. And that line is long and feeds up this gray PVC line and into the washer bath. So now, very manual from here on. Okay, so to get vacuum, we need the booster pump on, so it's about 140. We're going to open up this valve, and it's going to pull vacuum by pushing water through an ejector. So then sure, okay, let's go back and look at the sheet. Still not forming a sheet. Okay, you can see that it's starting to form a sheet now. We're going to collect all of that. I had some worries that this cook wasn't going to work out very well, but there are very few shives coming over here. So far, very few uncooked particles. You can see how dry it gets when it gets over to this side. There's a shive right there. Another little one over there. Okay, so I'm helping to stir it a little bit at the end here, but if you look at that sheet that's forming, it's actually quite nice. It's covering it just perfectly. Water jets hitting it there, there, and there. And then it's piling up at the end of the docking blade and dropping down into the wash stock tank. You can see the stock is a lot lighter in color. So the black liquor's been more or less taken out of it. Okay, we've finished the screening. It actually, or the washing, I'm sorry. It went quite well. We got a reasonably good sheet toward the end. Everything is empty. The number 2 stock tank is completely empty. Number 3, I'm sorry. And number 2 is now filled up with our washed fiber. Tomorrow, I'm going to run a consistency check on that tank. And then based on the consistency and based on the volume of the tank, I will be able to calculate how much yield we got. That is, how much fiber did we actually get from the cook. Because you remember that the liquor is supposed to dissolve the lignans, but it also dissolves the hemicellulose fibers. And if you leave it in there too long, then your yield goes down, down, down. Okay, we're good.